So our issue here is we have to connect magnetization to currents, because if we know the currents everywhere, we can get the magnetic field. Magnetization. And we're going to have bound surface and volume currents. Let's do this the old-fashioned way. Let's burn it. We've already seen the vector potential, even though I mangled it. It's 4 pi m cross r. This is from r hat over r cubed. This is equation number 11.
It's r vector.
It's r vector, thank you. Because it's b cross r. All right? Now, we're going to now say this is for 1, centered where? At the origin. 1, centered where? 1, centered where? At the origin. In other words, this is the vector potential. Here's the thing. Here's the z-axis. Here's the x-axis. Here's the y-axis. And here's r. If I want to know what A right there is, that's the source point. What's that? That's the field point, right? Now, in general, our goal is to calculate the magnetic field everywhere in space due to current distribution. All right? Be they bound, as we'll be doing in Chapter 9, or be they free, as we'll be doing later on. Okay? So,
do the bound surface have the same, like their dipole sticking out properties?
actually, it's what it is. It's not the dipole sticking out. If you think of this as a triangle, it's one little, think of them as squares, okay?
Okay.
It's one little leg that sticks out.
Okay.
One little leg out here that has no leg next to it. So it's not sticking out per se, it's just one end of the leg is different from the other side.
Okay.
Okay?
Okay.
Alright, or if you think of that way, you have more little, just remove the loops and just put the vectors in. And if you think about the bound ones, there's more magnetization up top than what there is below, so it's in that magnetization, and we'll connect those things. Okay, so we have that. Now we're going to do what we've done probably 30 times. Instead of having a single dipole here, suppose I have a bunch of dipoles over here. This is the source point. We call that r prime, correct? This is the field point. We call that r. I put a little volume around here, and I ask, what's the effect here? Okay? At the field point. What is A at this point? Call that P. Well, look, I have mu naught over 4 pi. What time we got?
101.
Holy mackerel. I wasted too much time doing that crappy thing just to show you I could. Okay.
Yay!
So this is M at r primed, because see, r primed is to the source point, right? D tau, call this dA. D tau, if you want to use D3R or whatever you want to call it, D tau primed. This is all the magnetic moments in there. That's the total magnetic moment in there. Magnetic moment per unit volume times volume gives you the total magnetic moment. This is no different. And now instead of having R down, and then this will have to be crossed into R minus R primed. D tau primed divided by R minus R primed cubed. You know what I've done there? I'll show you what I've done, but you guys are still, after 30 times, the 31st time is not any better. If I want to know what the electric field is from a point charge at the origin, I write down this. Let's use R. Agreed? That's the electric field right here from a point charge at the origin, right? Everybody with me? Is 1 over 4 pi epsilon naught is K. Suppose instead of this, I have a bunch of charge over here. Rho per unit volume at the source, rho r prime, yes? I want to know it over here at r, correct? Right? So what do? I find the little itty bitty amount of electric field due to this blob, which is K rho evaluated r primed d tau primed, right? It's the little volume in here, divided by the distance from there to there. That plays the role. I forgot that. Let's put that in first. R minus R prime. Then I can put the detail prime in, because I like to put the little skater piece at the end, just a matter of taste. R minus R prime cubed. Is that appreciably different than that? Not really. What's the only, and it's not really even a complication, it's a modification to the physics. That's a vector on that side, and that's a vector on that side. In this case, the vectorial property is carried by the distance. Here it's a little more complicated. The vectorial property is crossed into something else. But you see, it's the same thing. It's the same thing, all right? Now, I'm going to do some vector identities, and these can get a little bit involved, but I don't care. All right, let's have a look. It's a terrible thing to say. I do care, all right? I don't want you to get overly yeah. Ah! I care deeply.
We believe you.
No, I don't.
I don't care about you.
Of course
All
not.
right. Okay, so what are you laughing at?
That tone was kind of harsh there.
Yeah, well, you know, he's a grown man. All right, so in this case, I want to look at M R prime
I'm gonna go home and cry now.
cross R minus R prime. I want to look at this. And if you want to look where this is equation 13. We've done something like this before. This is equal to M grad of 1 over R minus R prime. Okay? And let's check we can do that again. I'm going to do this one more time because it has been a while since we've done it with respect to the prime variable. So another reason I wanted to make sure that I have that prime in there. Doing respect to the prime. Most of the mathematics of electricity and magnetism is throwing this gradient around and doing integrals over vector curves. Okay, at least for us. And this is I hat then minus 1/2. I'll have all that business to the power minus 3 halves. Then I'll get 2 x minus x primed I hat. Yes? But then, I'm taking the derivative to the prime to the unprimed. I feel like I should get some for the amount I'm going to hear you crunch down on those things. My God.
Sorry.
You take the derivative respect to the x prime.